Hi, this is Rich Terrell at Jet Propulsion Laboratory, back for continuing coverage of the Galileo arrival at Jupiter. We've had a successful morning, or actually afternoon, with the a successful lockup of the probe data with the orbiter. That mission is now completed, and that data is hopefully stored on Galileo spacecraft. Coming up will be the main orbit insertion, the Jupiter JOI, where we'll fire the engine at about 5:19 Pacific Standard Time. That is the Earth receive time. At 6:08, the engine will shut off, leaving Galileo in an orbit around Jupiter, and we'll have a wrap-up press conference at 6:45. To remind you again, you can contact us via the internet at www.jpl.nasa.gov or the Galileo homepage at www.jpl.nasa.gov/Galileo. FTP address is ftp.jpl.nasa.gov, and an electronic bulletin board at, with a modem on the phone number 818-354-1333. Also, we have a email address at newsdesk@jpl.nasa.gov, or you can fax us at 818-354-4537. Those home pages are pretty crowded right now, and good luck trying to get on them, but they will be available to you at any time after this as well. Joining me, we have several guests. We have Wes Huntress from NASA headquarters, the Associate Administrator of the Office of Space Science, Torrance Johnson, the Project Scientist for Galileo, and Bob Mitchell, the Science and Sequence Office Manager. Welcome, gentlemen. Had an incredible day so far, and still incredible things to come. Reactions?
What a rush.
What a rush is right.
One big one down, one more to go.
The big one to go. In fact, the big one to go is the main orbit engine burn, and that has happened, or that is happening right now, and we won't know about it for another few minutes because of the light time that it takes for these signals to get to the Earth, and that's 52 minutes at 500 million miles.
In fact, in this case, with the burn lasting 49 minutes, it'll be completely done before we see the beginning of it.
Right, right. And let's see, that 49-minute burn, when we see that image of the rocket going off, it's a 400-Newton engine. And give us an idea of what, is that a powerful acceleration? Is that a gentle nudge?
It's a pretty gentle nudge. Relative to the small thrusters that we've used to navigate so far, it's quite a bit bigger. Mm-hmm. But 400 newtons in what probably is more common units is about 100 pounds. And the spacecraft at this point is still massive enough that that amounts to about 1/40th of a G.
1/40.
So it's a pretty gentle ride.
Yeah, I
but
understand.
It is constant. It's not like we're bumping it like that. We're going to keep pushing it like that for 49 minutes. That's what's going to slow us down.
Right. Right. I understand that that would be a speed of about 0 to 60 in 2 minutes,
right, well,
which isn't very fast, but if you do that for 49 minutes at that acceleration,
right,
you're going to go pretty far.
Right.
Okay, do we have, we'd like to actually go around the laboratory right now and see what is going on at the MSA, the Mission Science Area, and we see that now, and Bill O'Neill should be there. Actually, we're going to try to get a link up with them. Are we ready for that, or we're not ready for that? We'll be going back there and looking at reactions for the engine burn, and that will be coming up shortly. Okay, Wes, you have.
Yeah, I'd like to kind of take this opportunity that you're all giving me here to welcome all the guests that have come here to JPL. And I've been coming to these things for a long time. I worked at the laboratory for 20 years, watching all these things happen from Mariner 6 all the way up through Voyager in '89, the last encounter at Neptune, Magellan, and now Galileo. And these things are always exciting. And so I'd like to especially welcome those who are coming for the first time and who have never seen, you know, the real human event that this is. I was out there for the probe entry, and I don't know if you've got to see the reaction yet there, but it was tumultuous, and it was the feelings were palpable. And you sit there and you're calm, you're waiting for it to happen, and as soon as that happens and you see Bill O'Neill's hands go up, behind the booth, it just wells up, and you can't help it. It's a wonderful experience. It happens, not that often. We're going to try to make it happen more often than it's happened in the past. And so I hope those of you who came here for the first time today get a chance to come back and see this kind of event happen in planetary exploration more often. And we're not done yet. We've got one more to go here yet.
Right, one more exciting event. Actually, two more, the engine on and the engine off.
Right.
Torrance, what's up for your, what's next for you in terms of the day's events?
Waiting for JOI is our big looking forward now. And as you said, we got to get JOI started. We got to get it stopped on time. That program is all on board. The spacecraft is operating beautifully. We have good signal from it. Every confidence that will work right. And then we'll be the first artificial satellite of Jupiter, and we can look forward to getting the probe data back in the next few weeks and months, and then looking forward to even beyond that horizon to next July, when we come in for our first ever encounter with one of the Jupiter moons, with our first Ganymede encounter in July.
Mm-hmm. Oh, that's going to be great. And it's a 2-year orbital tour.
2-year orbital tour, and we'll be taking data pretty much continuously. Once the data pipeline opens, when we get to Ganymede, we'll be getting data back virtually every day with really new, eye-opening things about the Jupiter system on the ground every day. And we expect to have a first look at the probe data even earlier than that, of course, by the 19th of December.
That's terrific. I understand we're ready for Bill O'Neill at the MSA. Bill, can you hear us?
Hello.
Hi, Bill. This is you're on camera. Give us a wave, and what's happening?
We'll all give you a wave, and we're having a great time here. I want to welcome everyone to the guest operations about to witness with us the momentous event of the first spacecraft going into orbit about Jupiter. And we are just ecstatic already because we have confirmed that indeed the probe was successful. It radiated a signal to us. The most difficult entry ever attempted has been accomplished. So it's just a wonderful afternoon, but a very well-earned afternoon. And you can see all of us here are just beaming with delight, but it's been a long time coming.
Well, you're all to be incredibly congratulated. It was a great monumental achievement, and we've got one more monumental achievement to go just today.
And that'll be pretty quickly now, and we're just about completed with the spin-up maneuver preparatory to lighting the main engine. And we have every reason to expect that we'll see another stunning performance from our German propulsion module.
Okay, we'll be looking over your shoulder in about another 10 minutes to see how things are going.
Roger that.
Okay, terrific. We're well on our way to receiving those signals for the Jupiter orbit insertion. I guess let's talk a little bit about that orbit insertion. It's a 49-minute burn, but I mean, if we burn for 40 minutes, would we still be happy? Would we still achieve Jupiter orbit? Or what is the leeway there?
There's not a lot of leeway, and if we burned for 40 minutes and stopped, we wouldn't be very happy. It takes the majority of the burn just to change the orbit from being a hyperbolic orbit to an elliptic orbit.
To capturing
Right,
the
right.
spacecraft.
The point to where it's captured and it'll stay in orbit about Jupiter requires that almost all the burn be done. And then just the last few minutes, very few minutes, are what bring it from a captured orbit down to the orbit that we need with a period of just a little over 200 days. Mm-hmm. So it's all got to happen.
So we really want to see those 49 minutes.
That's right.
We're pretty close to it.
That's right.
Good.
Yeah.
And,
Yeah, and I'm just anxious right now to see that Doppler plot and see the thing turn the corner and start going down there where it's supposed to go.
We all are. Believe me, we all are. In fact, let's go to David Seidel, who should be at the navigation's operations area. David, are you ready?
Yes, Rich. This is one of the places where people have a tremendous vested interest in what's going on. This is the Galileo
Hello, David.
navigation area. Yes, can you hear me, Rich? This is a This is the Galileo navigation area. These are the navigators have gotten the spacecraft through its Vega trajectory, Venus, Earth, and then Ida, Gaspra encounters, and then to Jupiter. They don't have any particular responsibilities per se at the moment. The spacecraft trajectory is well determined by the laws of physics, but they're on the edge of their seats because their future depends on the successful JOI burn, of course, as does the rest of the team. If we have a successful JOI burn, which everyone expects, then their work will begin anew because they have designed the orbital tour as the spacecraft orbits around Jupiter and flies by the moons, and they'll be refining and tweaking that so we get the best possible science at each of the encounters. And we'll be coming back to this site to get their reactions throughout the JOI burn.
Okay, thank you, David. Let's see, I think we're also going to have an animation now, and maybe Torrance, you can address that. This is the orbital tour, I believe, that we're going to be showing.
This is starting off, I think, with us being right over Jupiter. The animation now shows the 400 Newton engine lighting off, which we hope we'll get confirmation of in just a few minutes here. And then a few hours later, we go behind Jupiter, as seen from the Earth and the Sun, into the shadow of Jupiter, actually. This is an animation showing that. Now, we'll be continuing to measure the radio signal as we go behind Jupiter and come out again. That'll give us a lot of information about the upper atmosphere of Jupiter from what we call a radio occultation experiment. We've done these before, but as we know, Jupiter is a dynamic place. The clouds and structure of the atmosphere is different at different latitudes and different times, and so this will be one of our first steps to understanding the atmosphere of Jupiter just from using the radio signal that we're communicating with.
Oh, that's great. That's great. We've got actually a question here from the internet, and the question is, how many years is the orbiter expected to send data from the Jovian system?
Well, the nominal orbital mission, as we call it, that is the planned orbital mission, is approximately 24 months by the time we finish the mission. We'll be finishing our assigned mission in about December of 1997. And that will encompass 11 orbits or 11 encounters of satellites during the tour, plus a lot of other observations. Now, we probably won't run out of gas precisely on that date, and we'll still have power left. We believe that we've designed the spacecraft to survive the radiation environment. We don't know what we would do after that, but at some point fairly soon thereafter, we'd lose control over the spacecraft. And at that point, it's still a satellite of Jupiter, of course. It doesn't fall out of orbit or anything like that. But probably within the next few years or hundreds of years, it would either hit Jupiter's atmosphere or run into one of the satellites if it were uncontrolled. Bob may have an idea about approximately how long that would last. It depends a lot on what orbit we leave it in at the time we finish trying to control the spacecraft.
So after the nominal 2-year mission, there may be some attitude control fuel left over to do further
Right.
tours and further orbits.
Right.
One of the other questions we had, which actually kind of leads right into that, is first of all, it says congratulations on the Jupiter project, but it says, will there be another chance to get close-up views of Io after today?
Well, one thing to remember is that the mission did lose its very highest resolution views of Io that we had hoped to take today. But we had planned a very extensive study of Io during the entire mission. Io is a volcanic dynamic place. Its surface is changing every day. We know this from both the Voyager data and from studying it with telescopes and the Hubble Space Telescope from the Earth. And what we have to do with Galileo is a chance every month, essentially, to take a really close look at Io. And we come in very close to Io, actually, on every orbit. So we have, in essence, an Io volcano observatory built into the mission, and we're very excited about looking forward to that. Now, we will be looking toward the end of the tour at the possibilities for whether we could go back even closer to Io later on. In fact, even before we had the difficulty that stopped us from taking the data today on Io, we had been looking at that as a potential way to end the mission because Io has always been exciting to us.
Right.
But we don't know what we'll decide to do until after we're in orbit. We're hoping to have surprises and discoveries ahead of us, and exactly what we decide is the best thing to follow up on those discoveries will depend a lot on what we see. So everybody can stay tuned, take a look at it, and put their own vote in as what they think is interesting.
Terrific, terrific. Maybe we can even vote over the internet. We're We're coming up on about 3 minutes away from the time where we would expect to get confirmation that the engine is burning. Maybe we can look at the Doppler plot just to get an idea ahead of time on what we'll be looking at. And here it is. And Bob, maybe you want to explain a little bit about what we're seeing here, what we might expect to see?
Okay. Well, the line that you're seeing going across the top represents the difference between what we have predicted that we will see, knowing what the trajectory is going to be, and what we are actually seeing as the data comes in. The data is a frequency measurement. The spacecraft is transmitting a signal to us, a radio signal at a known frequency. But because of the speed, because of its motion relative to us along the line of sight, we actually see a different frequency than that. And so what we're showing here is the difference between the frequency that we really see and what we predicted that we would see.
So this translates directly into a change in velocity in the spacecraft as this changes from that line.
So when we see a change from that line, we're going to know that something going on in the spacecraft, that the engine is burning.
That is right.
Right.
Now, normally, if we kept going with this predicted behavior all the way across, you'd see nothing but a straight line all the way across.
Right.
But seeing nothing isn't very reassuring. When something happens, you'd like to see something change.
Right. We're going to go to some reaction shots around the laboratory as people anxiously await what's going on. This is Von Karman Auditorium, and they're watching the clock and watching that same Doppler plot we are.
That's good enough. There are propulsion people down in front. This is the nav conference area. you're seeing right now is the difference between what we would have gotten had the engine not fired and the actual data coming back from the spacecraft. So that says something's happening right now on the spacecraft, which is moving it, and that is the engine firing.
You're going to be audio. No. Go back to you.
Okay, hi, well, we've done it. We've got confirmation of the Galileo orbit insertion burn, at least beginning. We've got 49 minutes of that to go before we'll really be in a safe orbit around Jupiter. So it's a very, very exciting moment. The second big hurdle of the day, the engine starting, and now we just have to wait and make sure it fires long enough. Torrance, you waited a long time for this moment.
It's really great to be having got to our target, and now we're going to stay at our target.
We're going to stay at our target, hopefully. Hopefully, we're well on the way there. The Doppler plot looked good. Was it as expected?
Yes, yeah. So far, it's just exactly as expected. It looks like it's doing just the right thing. You always have to wonder if you really think it's going to work, but until you really see it, it's a bit of a concern.
Let's. Can we go to the MSA and find a reaction there? Hello. Whoop. You just hung up.
We'll come back to you.
Okay.
Go ahead.
Hi, we're on our way trying to contact the mission support area. And can you guys hear us over at the MSA? Over. Hello, can you hear us at the MSA?
Are you reading me? This is Neil Osmond in the MSA.
Hey Neil, we read you clearly. Congratulations.
Thanks a lot. Everything's going good so far. We spun up as we expected to about 10.42 RPM, and the maneuver started right on time, and everything looks great so far.
Okay, so now we just wait and find out whether we get the 49-minute burn.
That's right. That's the scheduled burn, and you'll see it first on the Doppler plots, which I guess you guys are broadcasting into all the rooms.
Right, we're looking at that right now, and it looks good. Very, very clean signal.
Right, and you can see a little arrow at the bottom of that, which is the cutoff. That's the point we're aiming at. If we get real close to that, it'll be a great burn.
Terrific. Once again, congratulations to everyone there on the team. Done a great job.
Thanks a lot.
All right.
One thing we might point out is that when we get down to that arrow that Neil was talking about, where we're going to turn the corner and level out again like it is up on top, we fully expect that we will lose lock with the DSN because of the change in frequency that's going to occur, and because we don't know exactly where that occurs to tell the DSN. So if this signal goes away for a little while, people shouldn't take it down by that arrow by the corner. That shouldn't be a cause for alarm. We expect that to happen.
Okay, and that lock is because the Galileo is now going to change its velocity with respect to the Earth as the engine cuts off, and you're actually tracking a different Doppler signature?
Yes, kind of like that. When we generate the predicts that we give to the station that they use to track, those predicts have to be very accurate. And we don't know just exactly where the burn is going to end because there are minor variations in the thrust level. The accelerometers will measure that and cut it off at exactly the right point. But we don't know just exactly in time where that's going to occur. So the predicts that we've given to the DSN probably aren't going to match exactly where it cuts off.
And, okay, and that's because now you have accelerometers on board the spacecraft, which we're actually going to measure. Once it's got enough push, it'll shut the engines off. Right?
Yes,
So,
right. Yes.
So we'll get that accurately. The official time is 5:20 Pacific Standard Time. The engine, we received confirmation that the 400 Newton engine started as planned. It's a 49-minute burn, should burn till 6:08 p.m. And again, as you pointed out, the communications is expected to drop out momentarily when that burn is finished, but that is expected.
You know, it's interesting. I was noting on the timeline here, Rich, going back to the other part of this mission, the probe, He said at the time when JOI was initiating on the orbiter, the probe had already lost its parachute, was dropping into the atmosphere of Jupiter deeper, and the aluminum metal inside the probe was beginning to melt.
That's right.
So the probe that was with us earlier in the afternoon is rapidly in the process of becoming part of the atmosphere.
That's right. That's right. It's rather fitting. Part of Galileo becomes part of Jupiter. And so we're continuing our coverage now, and again, it's 49 minutes. We expect the burn to last until about 6:08 p.m. If it lasts that long, then we're going to be confirmed in orbit around Jupiter. We'd like to go to the visitor center now with David Seidel, and are we ready for his interview? No, we're not. Okay, well, we'll stay here, and hopefully we'll get an interview with Don Williams, one of the shuttle astronauts that actually deployed the Galileo spacecraft. What else can you tell me about JOI that we should know?
This is just kind of a watch and wait period for all of us, you know. It's kind of interesting thinking about this. You think about rocket launches as being things that go boom, and you know, the thing goes up.
It's just a gentle push.
This is a gentle push, and it just lasts a long time. And we're just sitting here like everybody else. Spacecraft, I think that one thing that we should keep noting is the spacecraft programs, the computer programs on board the spacecraft that have been running the spacecraft all day long, have just been clocking out absolutely perfectly. I mean, we had all had some worries that things like radiation in the environment near Jupiter might have disrupted some of those programs. The artificial intelligence on board the spacecraft is capable of handling that and continuing with its job anyway. But it's always nice not to have it do that. And the spacecraft has been behaving very well. It means that the engineering designs that went into those components, the electronics and the way the computers work that are telling the engines when to burn and how to burn and so forth, are also performing beautifully. And I think that bodes very well for the rest of the mission.
And do you think that this is a measure of conservatism in the way the thing was designed, or could there be a real change in the radiation environment about Jupiter? I mean, we have seen changes in some of the other environments as well.
Everything we know from measurements of the radio fluxes from Jupiter, for instance, and the Ioplasma torus from the Earth suggests that the radiation belts of Jupiter are still just as fearsome as they were before. I think this is just good engineering design. Once we get data from our instruments on board, of course, we'll know more about the changes that might have occurred and so forth. But no, I think this just says that the design people did it right. We've got good parts, and the parts are reacting as expected, which is not at all to the radiation environment.
All right. Well, we actually have a question from Escondido, California, over the internet. Actually, it was a fax, and it says, speeds, temperatures, and radiations of Galileo encounters at Jupiter sound lethal, yet the spacecraft survives it all. Well, thank goodness for that. Is there any chance that a space vehicle could orbit or land on one of Jupiter's moons one day, carrying humans to explore these remarkable worlds, or is it too deadly a place for human beings to go physically?
Well, the answer to the first question is it certainly is possible for a spacecraft to land on the surface of these satellites. Galileo is coming close to that. The velocities at which we go by these moons are not that great, and by future spacecraft carrying probes with some deceleration capability could put something on the surface. It's going to be a long time before I think we were prepared to send humans there, however, because as the correspondent mentions, is that the environment really is deadly. The radiation belts are deadly. One would have to carry massive amounts of shielding to protect any future astronauts in those environments. Perhaps Callisto, maybe Callisto.
Maybe Callisto.
And I heard a science fiction writer say once, if an engineer tells you he can't do something because it violates the laws of physics, you might believe him. But if he says it's just very, very difficult, it'll probably be done. So going to Jupiter's moons with humans is very, very difficult, but not impossible.
Great. We'd like to roll a reaction shot tape of reaction during the probe entry.
Trouble with Don Williams, but I think they can. 3 minutes, 20 seconds.
over on the screen there, still tracking down right.
Congratulations, Bernie. You did a good job. 2 decades worth, huh? Yeah, 2 decades worth of good job. Worrying about whether we tried to harness that good enough or not. See, I knew. I told you this is going to work. Don't worry. So you want me to go up there? You glad you stuck around? Yeah. Till the end of the mission? Yeah. Man, it was right there. There was no ambiguity at all. Nothing to it, right? I would gold looks good. Wow. Told you. Yeah, I got another good one. Second readout is good. Second is good. Can you make me a print out and take upstairs? Okay, want me to go upstairs and talk to you? Let's go.
Probe confirmed 693.
That's it. That's the confirmation. That was a single yes or no. Okay, one down.
That was a call from the probe engineering team chief, Pat Melia, which said very simply that we had indications that the orbiter receiver had locked on to a signal. Of course, we presume it's from the probe. So.
The ELA is going to try to pick up the probe signal directly.
Hi, we're back live. Andy Ingersoll has joined us, and Dr. Ed Stone, the director of JPL. Welcome. Ed, this must be a proud day for you.
Well, this is an exciting day. This is what it's all about. This is what everybody works so hard to make happen, and it's happened today, so it's a great day.
This has been a long time coming. I mean, it was a torturous way to get to Jupiter, but we're finally there.
Yeah, well, and you know, given where we were in 1986, where it wasn't clear there was any way to get to Jupiter with Galileo, and now it's clear we found a way, and it looks like we're going to be in orbit, and we're going to have a wonderful 2-year tour of the Jovian system.
When we got to Jupiter, we just want to make sure we stay there.
Yeah, that's right.
And that's happening right now. The Doppler plots look good. They are still going as predicted, and you can see them now. The small little arrow at the bottom right corner is where we want to be. So we're about a third of the way there. Not enough to achieve orbit, but at least everything is going nominally, and things are looking very good. Andy, another milestone.
Just like old times.
Yeah, actually, there are a lot of Voyager veterans here. Let's talk a little bit about Voyager. That was the most incredible, electric moment of being and flying past the Jupiter system. And I think all of us got a real taste of really wanting to go back. After the second flyby, we said goodbye to Jupiter. We couldn't wait until Galileo got there. And finally, that moment's here. You want to compare the kinds of things we learned there and the kind of things we might expect, Ed?
Well, I think that what the Voyager at Jupiter really showed us was how different the outer solar system was than our sort of simple expectations were, and really set the stage for a whole series of discoveries as we moved out into the solar system. But Jupiter really opened our eyes. We had some very simple ideas about what we were going to see, and nature was just dramatically more interesting. And that, of course, is what Galileo will have a chance to probe in much more detail. Being there, staying there, rather than just flying by with snapshots and a few other bits and pieces of data in a short period of time. We're going to have 2 years at least to really explore at much higher resolution, much greater detail, the diversity which Voyager really revealed in 1979.
Mm-hmm.
Yeah, I would say, given all that we know about the Earth and all the effort we've spent studying the Earth, extrapolating that to
Jupiter and its satellites was just, it taught humility because we couldn't extrapolate very well.
It really did. As I said, I think if there was one thing that we could expect, that we grew to expect during these encounters, was to expect to be surprised. I mean, we were just blown away, one thing after the other. And I'm sure there are a lot of plums still to capture with
And the
with
Jupiter
Galileo.
encounter really was the start of that. I mean, I remember, Ed, when we were originally thinking about strategies for looking at the moons of Jupiter, people thought, well, it might be okay to look at an ice moon and a rock moon, but then we'd have sampled everything. And when we saw that tremendous diversity there, it's one of the things that drive us to go back and look and try to understand. And I think the same is true of the environment. If you think about going back to Pioneer, we really found out what that radiation belt was like there in terms of what we might have to experience with our electronics. Tried to harden Voyager to survive in that environment, and I remember going by Io was real white knuckles time back then. So that we had glitches going on in the flight computers and so forth, and went back again with Galileo and thought real hard about how to exist for 2 years in that environment.
Yeah, that must have been a pretty scary time
It
for
was.
you as well.
You always take a risk when you go into an environment like Jupiter's because you can't really test the spacecraft at the level it's going to be exposed because you use up too much of its radiation lifetime. So you're extrapolating your experience, saying that it should survive, and the Voyager did survive, although we did have a few little glitches, which affected things, not seriously, fortunately. And Voyager 2, we purposely moved further out as Galileo is moving further out for most of its orbit in order to minimize the risk that we were taking with Voyager 2, which was the spacecraft we definitely wanted to send on to Uranus and Neptune.
Mm-hmm. Right, right. But now we've got a spacecraft in orbit, hopefully in orbit, or very close to being in orbit. Let's go to the mission director, Neil Osmond, and see if we can get some other reactions there. Neil, can you hear us?
Yes, I can.
Okay, how's the burn going? We're looking at the Doppler plot occasionally, and things look good here. How's it look there?
About 9.5 minutes into the burn, we were 0.4% under burn. As of right now, well, our telemetry is lagging a little bit as expected, but we've completed at least 146 meters per second of the burn, and it's looking great.
Oh, that's great. 0.4% is wonderful. That's just right nominal.
It sure is.
Okay, well, keep us posted, and we'll be looking for reactions on the burn cutoff later. Thanks very much. All right, things are still going. It's still going, like the battery commercials do. What else? Let's go back and discuss Voyager a little bit. I mean, there were some real surprises on some of the things, particularly at Io and Europa. Galileo hopefully is going to fill in some of those holes, and I understand that the resolution is quite a quantum leap from what we got from Voyager.
Oh, with respect to the satellites in particular, and Andy can speak to the atmospheres, that the satellites, the Voyager views were so stunning that we forget how crude they were in some sense, is that they were mostly global views with the resolution of a kilometer or a few kilometers. That's equivalent to a global meteorological picture of the Earth from a weather satellite, which is great for looking at some things, but you can't see much detail down there on the ground. With Galileo, we go from that perspective to the perspective of something with Landsat resolution. That's going to be a real eye-opener for people interested in the geology of the planet. Now, with the atmosphere, of course, things move. And Andy's the expert in that, and we've got a really good survey of things in the atmosphere at resolutions better than actually we looked with Voyager for those types of phenomena.
Right, besides the probe where we get down below the cloud tops, we've got a suite of instruments that's never been assembled to look at an outer planet, different wavelengths, and we're going to probe beneath the clouds and hopefully we'll understand the weather.
Right. We're going to look at a video right now of the Voyager 2 encounter with Jupiter, and maybe we want to, Ed, maybe you want to narrate this and You've
Now, the
seen this
Voyager
before.
2 encounter, we actually we had 3 months, basically between March and July, to reprogram some parts of the sequence on Voyager 2 so that we could look more closely at the recently discovered volcanic plumes on Io. So it was quite a scramble, as I recall, doing the reprogram. We had not intended to reprogram. But it was such an exciting discovery, an unexpected discovery, that we did change the sequence at the last minute to try to recover that bit of data. And of course, it was Voyager 2 which gave us our first close-up, for Voyager at least, close-up look at Europa. Voyager 1 saw Europa at a great distance, and we knew it was white from Earth-based data. It had some peculiar markings on it, but when Voyager 2 flew by at its distance, it really became very clear how interesting and different Europa is than any other body in the solar system.
Maybe we can call up an image of Europa from the library that we have, and we can talk a little bit about this. I understand that the difference in resolution from Europa that we had from Voyager to what we're going to get from Galileo is equivalent to taking a book and reading it from the top of the Empire State Building if it was on the ground floor versus having it in your hand reading it. I mean, it's just an extraordinary difference in resolution.
MD, this is Nav on MDNet.
Roger.
Oops. Okay, I guess we don't have a Europa picture, but anyway, Europa, why don't you tell us a little bit about Europa, Torrance? And,
Europa is, to me, one of the strangest of the moons of Jupiter. One of the strangest moons anywhere, actually. It's about the size of our own moon, but it looks totally different. Instead of being covered with a battered old surface of ancient lava flows, it's covered with sparkling white ice. And that ice has got huge cracks in it running for hundreds of thousands of miles across the surface. And Europa is also heated by the tides of Jupiter, as Io is. Not as much, but enough probably to keep water liquid underneath that ice cover. And that's one of the things that we're really looking for, to try to understand what's going on with Europa, how thick that ice is, and whether in fact Europa is covering itself up with new flows of ice continually. One of the things that's developed in the past few years is a better understanding of how often things hit Jupiter. Comet Shoemaker-Levy 9 was a good example.
Right.
And given Gene Shoemaker's latest estimates of how often things hit Jupiter and therefore Europa, it makes the surface of Europa perhaps very, very young, perhaps just millions of years old, perhaps yesterday.
There's a surface view of Europa. With,
that
kind of a
shows
strange...
almost very smooth, you notice. There are no mountains sticking up through that ice. There are only 4 or 5 impact craters that you can see instead of the huge impact scars that you see across the surface of most of the other moons out there. Europa's surface is almost entirely dominated by these linear features and ridges on the surface. There's nothing on Europa's surface that we saw with Voyager that was higher than just a couple of hundred yards high.
Mm-hmm. So the lack of craters...
No mountains, no craters, just ice.
So it looks like just ice. So
very smooth ice.
Very smooth
Europa
ice.
on the rocks. But the lack of craters really indicates that perhaps the surface is very young, or there's something that modifies it very easily.
Something has to be removing the craters. And if comets are the major thing hitting the system, like we think they are, then we should have expected, if the surface were as old, for instance, as the lunar Mare, to see many, many more craters from comets hitting the surface. The fact that you don't see them there suggests that that surface and the geology underneath it has been active. And easiest way we can imagine for that to be geologically active is to have liquid water under that ice.
So we could have a second volcanically active body around Jupiter with...
right, only in this case the volcanoes may be on the floor of the ocean and we may be seeing ice volcanism as a result of those things.
Right, actually incredible. We're looking at the MSA and we're still waiting on till about 6:08 until we get the
Like we're about halfway
engine.
there.
Looks like, yeah, we're about halfway there. Again, moving toward that arrow on the lower right side. And things look good. Looks like it's going toward the arrow. Here's a view of the Galilean satellites compared to some other things. And maybe you want to say a few words about the size of these bodies. They're really planetary-sized bodies.
Yeah, this compares some of the planets that we're familiar with. This is our own Earth, of course. Here's Venus, essentially the twin in size, but of course very different, as the Magellan spacecraft showed us. Then we have our own Moon down here, Mercury, and Mars here. The 4 Galilean satellites are here: Io, Europa, Ganymede, and Callisto. If these things were orbiting around the Sun closer to us than Jupiter, we'd have been sending Mariner Ios, Mariner Ganymedes to
and we'd be
visit
calling
these
them
things.
planets.
And one of the really neat things about these gravity assist techniques and having a spacecraft in orbit around Jupiter is we basically get what amounts to a cut rate orbiter of each one of these satellites, since we go very close to these satellites on every orbit while we are orbiting Jupiter.
Mm-hmm.
It's a real force multiplier.
It's really going to be quite a bonanza there. So the each time you fly by one of these things, you can modify the orbital tour and get back to another encounter.
Yeah, we used to like to say that Voyager was sort of like a 4 or 5 cushion billiard shot to get out to Neptune and beyond. This is an 11 cushion billiard shot. You thread the needle with the first encounter, and after that, the orbit does its thing, with small perturbations that we have to worry about with our engines.
Little tweaks. Is there any concern, or was there any concern in flying so close to Io? We flew within about 1,000 kilometers.
1,000 kilometers.
Was there any concern about running into material?
We looked at that early on. As you're aware, the plumes on Io that we observed with Voyager, we saw go up to altitudes of about 300 kilometers, basically, was the highest ones we saw. And the physics of what drives those plumes is apparently that they're huge geysers. We don't think that geysers on Io, given the energy sources there, can get higher than that. Mm-hmm. We still didn't want to go right down at 400 kilometers, so we thought 1,000 kilometers was pretty good.
Okay. Okay. Let's see. We can. We're looking at the MSA now, and again, people are waiting on looking at the Doppler plot, the same one that we were looking at. Still waiting to see, well, hopefully not seeing any deviations in it until we get to the full 49 minutes of that plot, but things still appear to be looking good. We got a question, another question from the internet. Actually, it was faxed to us, and maybe I can ask what type of propellants is the orbital insertion burn on Galileo? We've seen those animations of the burn, but what are we burning?
Well, the fuel that we're burning is monomethylhydrazine. And the oxidizer, which we have to take along because there's no oxygen there to make the fuel burn, is nitrogen tetroxide.
Okay, not the kind of things you get at the gas station.
That's right, not what you get at the gas station.
But these are fairly common propellants that are
these are very common for space applications. They ignite on contact, so that once they meet in the combustion chamber and burn, the process just keeps going.
Okay, so so you just mix them together, they burn, and that's it.
That's it.
This German rocket design, in fact, was based on a design that was successfully used in Earth orbit on many missions. And so this is a common type of rocket. What makes it uncommon is it's out at Jupiter now.
Right, right. And we're looking now at, I think, the navigation area. And, people are, again, still waiting on confirmation of the burn cutoff. It will be quite a few minutes before that happens, but we're still looking at the lab and looking toward that area. Okay, and so what can I say? I mean, everyone's getting really nervous on waiting on this. This is the last big event of the day, or is the last big event. We still have the occultation 9 hours after this, where we go behind Jupiter. Will be measurements taken there in the shadow?
Yes, there will be. We won't have a lot of data on them until the radio scientists analyze those data. What we're doing is with other spacecraft that have gone behind Jupiter is we're measuring the way the radio signal changes as it goes into Jupiter's atmosphere, seen from the Earth, and then emerges from Jupiter's atmosphere. So this will be our first look at the upper atmosphere of Jupiter and the ionosphere of Jupiter on the mission. We ought to have some information on that in the next couple of weeks as the radio team analyzes those data.
Because that data is on the ground. That data is
right
Galileo
here.
signal
That's right.
coming to the ground,
That's
so
right.
we'll have that, and that'll
So
come.
we're actually using our communications device to make another type of scientific investigation.
Right.
That actually is the way we first discovered Io had an atmosphere. It was passing the radio signal from Pioneer 10 through that very tenuous atmosphere.
And we're going to be doing that again on this mission with Io also, so that we'll have another look at how variable the ionosphere of Io is also.
Okay. I know all of you want to get back to things. It's been a long day for some of you. Like I said, you were up at 4 o'clock in the morning giving interviews, and Torrance, you're probably doing the same. Any final closing remarks?
Well, I think this, as I said, is really what it's all about. I mean, this is really what the space program brings. It brings the opportunity to see things nobody's seen before, to learn new things, and to understand how the solar system, how the planets, how it all works. And I think this is the beginning of a wonderful 2-year journey.
Great.
It's pure discovery.
Okay. Well, thanks very much for being here. Hi, we're back now with Torrance Johnson and Carl Sagan. We are at the top of the hour. We're about 6 minutes away from the end of the burn. Torrance tells me that if we burn for another 4 or 5 minutes, we'll probably be in a safe orbit around Jupiter, but we really want to do the nominal 49-minute burn. And I think things are going still very well. If we look at the Doppler plot, we can see that we are inching our way toward the bottom of the screen there and getting toward that area. Well, the arrow's moving. Anyway, once that plot flattens out in a line parallel to the top line, we will be there. We will be in orbit around Jupiter for starting our 2-year tour.
And remembering that we may have a period of being out of lock with the signal because of the change in frequency right at the end of the burn.
Right. Carl, welcome.
Thank you.
It's good to see you here.
Thank you. Happy to be here.
Another encounter.
Another encounter.
Another notch in your belt.
Well, another great encounter. And I'm just so glad that after all these perils of Pauline that the entry probe entered, that the tape recorder is recording, that the burn to achieve orbital insertion is burning. All that's just terrific good news.
Give us a perspective on your reaction to the probe data. I mean, that's really the plum in this whole day.
Oh yeah, it's the conceptual novelty. I mean, we have flown through the Jupiter system before, 4 spacecraft. None of them can hold a candle to what Galileo will do, but still, it's not a conceptual novelty, although orbiting a Jovian planet is. But an entry probe into a Jovian planet, that is a conceptual novelty, and there we'll no longer have to deduce from chemical equilibrium where the clouds are. We will pass through the clouds. We will be able to see the particles and the dilution of sunlight. We won't have to guess what the chemistry, and especially the organic chemistry, is. We'll have actual data, hands-on data. I mean, it's really epical in the history of planetary exploration. The whole mission is.
We're literally feeling the wind on our faces in terms of the probe.
That's right. Well, not literally, but
well, figuratively.
Figuratively we are. The spacecraft is literally, and we're figuratively.
Right.
And I think it's really significant too, Carl, that this is a totally different type of atmosphere. I mean, we have put entry probes into Venus and obviously the Earth and into Mars. And those are all very interesting atmospheres, but evolved atmospheres. Jupiter's is the first time we've looked at anything like this that goes back that far with so little change.
Well, where the major constituents are unevolved, but the minor constituents might be highly
very
evolved.
interesting history, maybe.
Yeah.
We're going to briefly go over to the navigations area, see what's going on there with David Seidel. David, can you hear us?
Sure can, Rich. And with me is Dr. Jenny Johansson of the navigation team. And Rich, a moment ago, likened the having wind in your face, and I guess that's kind of the feeling of exhilaration that you guys must feel. How does it look to you from your position here?
Things look pretty good. I think everything looks, at least they're tracking the spacecraft. It looks pretty good.
And
we have a slight underperformance, but we'll be watching very carefully now where we're going to cut off the burn.
Okay, and if there's an underperformance or whatever, what's the responsibility of this team at that point?
Well, we'll be designing OTM1 or deciding whether there should be an OTM1. Everything enters in whether the Io flyby is as we thought it was, low, and whether the performance is under or over what is expected.
So it's a matter of taking accounting of all the performance factors that went into the spacecraft trajectory and then designing the next part of the trajectory. Explain an OTM?
We have our first correction maneuver on Saturday, and that's our first orbit trim maneuver, OTM1, and so we'll be designing that But there's a good possibility that we may not end up doing it. We may go to a slightly different Ganymede 1 date, and therefore we wouldn't need to do an OTM-1.
So the team goes back to work then?
We'll be working tonight, for sure, but the decision would be made later,
Great.
tomorrow.
Well, thank you and congratulations. And just to set the scene, since we were here earlier in the afternoon, it's gotten more crowded in here, and I wouldn't say that everyone is perfectly silent. I think the good measure is there's about 15 M&Ms left. When the M&Ms are gone, the spacecraft will be in orbit. Back to you, Rich.
Thanks a lot, Dave. Let's go around to the lab and see how people are reacting to the waiting for the news. This is Von Karman Auditorium, and people are patiently waiting for the engine cutoff. Again, the final moment. This is the mission support area.
At this point, a rough educated guess would be that we are now in orbit around Jupiter. We've burned sufficiently long to be in orbit. And the burn should continue. The burn should be continuing for at least another couple minutes and getting us in exactly the kind of orbit we want to be in around Jupiter.
Okay, so far so good, and we've now achieved enough burn to get us into orbit. We are now an artificial satellite of the Jupiter system. We now have to wait to make sure that the engine cuts off at the right time so that the orbital tour can be conducted properly. I guess if we cut off too early, the initial orbit around Jupiter would be much longer than the 200 days for the nominal orbit, and so we don't want to do that. We want to keep that burn as close to nominal as possible so that we don't have to correct that later on with fuel.
Right. So our fuel propellant budget is one of our major things that we keep an eye on because it means the resource to do science with once we're in orbit, to do the tour, to do these billiard shots.
Okay, we're coming up on about another 2 minutes for the engine cutoff. Mission support area, everyone watching the Doppler plot. New data point comes every 6 seconds. This is the Doppler plot. And remember that we may lose lock when the engine cuts off, which is normal. It's expected. The accelerometers on the spacecraft right now are measuring the amount of acceleration achieved when they determine that Galileo has enough acceleration. They'll cut the engines off. We're waiting on that moment right now. It's the mission support area. People are waiting on that. Obviously nervously bouncing around as we are here in the studio, as everyone is all over the lab. Doppler plot is still indicating, oh, we've got something. We've got an engine cut off. Okay, we've got absolute confirmation we are there. We've had a successful burn. We're having reactions around the laboratory. And as the NASA Administrator, Dan Golden, in the spotlights.
Oh, we're there and we're going to stay there.
We're there. This is great. And I say everybody is very, very happy right now. The big push, the big events of the day have now occurred, and they've occurred successfully. Let's see if we can get in contact with Bill O'Neill. He must be pretty happy. Bill, can you hear us there?
Yes, we can hear you fine, and it is my distinct pleasure to declare not only are we in orbit, but we're in a very good orbit. We're absolutely ecstatic. Our two momentous events of the day are now accomplished, and we have a great mission ahead of us.
So we had cut off on the engine from the gyros then, right?
Accelerometers is, we're confirming that momentarily, but the indication is accelerometer cutoff, yes.
Okay, that's very, very good news. And again, congratulations to everybody. This has been a monumental day.
You bet. 2 monuments. Thank you.
When there was, when orbital ignition began, but not yet achieving orbit, Dan Golden was giving high fives to people who I don't think had ever had a high five in their lives.
It looks like this was extremely precise. That's, a lot of credit goes to our German colleagues and the precision of that rocket and the machine that they built, and all of our attitude control and mission team engineers. It looks like everything was right on the money.
And it all working after such a long period of time in space.
Yes.
That's right, space and on the ground.
And on the ground, unanticipated delays.
Well, this has been a big day for Jupiter as well as for us. It saw its first artificial shooting star, and now it has its first artificial satellite.
I suspect Jupiter is very blasé about such event stars.
Well, actually, give us a little bit of perspective on that. A lot of the questions we get are, is Galileo going to search for life? What are the prospects of life in the Jovian system? And maybe you can give us a little bit of a perspective on that.
Well, I mean, the first thing to say is that nobody knows, and if we did know, you would have heard about it before now. But I don't think it's out of the question. It's not something to be dismissed by contemplating your navel. You dismiss it by doing investigations, and Galileo turns out to be a very powerful instrument. Where might we look? The possible subsurface ocean of Europa that you guys were talking about before is a very interesting environment. If there's liquid water, it's roughly room temperature. It's in the dark, all right, but there are cracks and maybe light gets down, and beyond that we now know of ecosystems on the Earth that live in the dark in the ocean bottoms. And while we're not going to send some part of Galileo down subsurface, there's a very good chance of elucidating much better our knowledge of what's happening on Europa. Then on Jupiter, the minimal statement you might make safely is that organic chemistry is happening. We know of some simple hydrocarbons in the atmosphere. We know from laboratory simulations, our laboratory at Cornell and elsewhere, that if you UV irradiate or charged particle irradiate or lightning irradiate a Jovian atmosphere, you get a very nice mixture of complex organics. And
including amino acids.
Including amino acids if you're down in the liquid water clouds. Now we have almost no data from the liquid water clouds. We're not only going to have data from there, we're going to have a probe passing into it, through it, and getting organic chemistry from somewhere in the vicinity of it. So even if the abundance of organic chemicals in the free atmosphere is low, because of lightning in the water clouds and for other reasons, you might expect there to be higher amounts in the water clouds. That's going to be very exciting. And if there isn't any organic chemistry there, that's very interesting. How come, why not? And then the most wild speculation, which I can legitimately describe it as such since I did it with my colleague Salpeter of Cornell, is that there might be life in the atmosphere of Jupiter. And if there is substantial organic chemistry and there's stuff to eat, and there are ways that are easy to imagine of organisms not being rapidly carried down to their depths at, great depths. No guarantee, of course, and certainly no guarantee that we would find it, but still it's a possibility to bear in mind. Even if there were no organic chemistry and no biological possibilities, Galileo is going to do wonders. From my point of view, it's sort of like it's your birthday, and your parents have permitted you to see that there's this big pile of presents, but you can't open them yet. That's right. And you're going to have to open them slowly on pre-assigned times. And that's the story we're in. We don't know what's in them, but we know that it's going to be great.
And they'll let you run through the room a few days earlier to see those presents. You want to go back and start unwrapping them.
Right. And you can't. The absolute law of nature that it's not permitted until a certain time. And that's the same situation we're in. Yeah. Another thing I think about, Rich, is, only 1,000 years ago, nobody thought of Jupiter as a world. It was a point of light in the sky. It was a god. It was a spirit. It wasn't a place. And we really knew nothing about it. Cultures all over the world identified it with the king of the gods. Well, it's not the king of the gods. We're quite sure of that now. But look what it is. It's this giant world, a kind of star that failed. And as Torrance said a moment ago, very different from the Earth and the other inner planets in the solar system. And there we are at it, finding out what it's about. And in just this last few months, there has been a credible announcement of a discovery of another Jupiter-like planet around a very different star, 51 Pegasi.
That's right.
And so what we're doing here is not just studying the Jupiter in our system, but in a certain sense, the whole category of Jupiters, of which, if the 51 Pegasi discovery is right, there must be an enormous number around nearby stars. So there's a whole new genre, category of things to explore. It's an epochal time in the history of human exploration.
That's great. That's exactly right. We've reached a threshold in terms of exploring our own solar system and discovering worlds around other planets, around other stars. And as you said, the discovery around 51 Pegasus was indication of a spectrum around that world exactly like the spectrum we're seeing at Jupiter. Methane gas in that atmosphere.
No, not in 51 Pegasus.
that's
that was this
Lisa.
Giese.
Yes.
Oh, we're discovering too many solar systems.
It's
Yeah,
hard
I mean,
to
it's
keep
just-
up.
it's all of a sudden, the last month, suddenly we have enough extrasolar planets to get confused over. That's, what better world?
But I mean, the technology has now, in many different approaches, reached the threshold. And there's a bunch of other ways of detecting planets around other stars that are just slightly sub-threshold right now. In the next few years, we'll see them achieve threshold. So in 20 years, we might actually inventory the planetary systems around hundreds of other stars, and then think how much perspective we will have on our own system, whether it's very common, this is the way systems always are, or whether it's just one of a very broad variety of systems, maybe ours even idiosyncratic.
Yeah, I remember when I was a kid, we talked about the formation of the planets, and it was always some extraordinary event. Some star nearly crashed into our star and set off a flare that created our solar system. And now I guess we've come to discover that the process of planetary formation may actually be something very common. And we're starting to understand that within our own solar system, and we're starting to see that in other solar systems, and other stellar systems as well.
Yeah, and that's part of the whole evolution since Copernicus, away from us being unique, the center of the universe, the reason that there is a universe, and the growing perception that in almost every respect we are a cosmic commonplace.
It's great to be average, isn't it? With the prospect of having other worlds out there, perhaps even similar to our own, and perhaps even inhabited.
Absolutely, and the technology for detecting other life is almost in hand on planets of other stars.
That's right. I mean, once we can separate the light from the parent star from the light of the planet, then we can start to make spectral measurements and look for disequilibrium products in the kinds
Exactly.
of signatures that may be common to biological processes.
Exactly. It's a very exciting moment to be alive and interested in these issues.
This is great.
And who can be interested? You got to be made of wood not to want to know where your planet comes from, where you come from.
That's right. You know, I'm often asked the question whether I believe there's life out there, and when you think of the enormity of numbers, the fact that there are hundreds of billions of stars in our galaxy and hundreds of billions of galaxies. Quite literally, there are more stars, more potential sites for planets and life than there are grains of sand on all the beaches of this planet. And you know, if you go to the beach and run those grains of sand through your hand, you'd have to be crazy to believe we're the only ones out here.
I mean, it's barely possible, but to conclude that we're unique is crazy.
Yeah,
I think it's very important to go back to the point Carl made earlier too, is the way you advance in these areas is to make measurements, not just theorize and speculate. And that's what we're about to do with Galileo, looking at our own system. I mean, to find out not just what we think might be there, but what is there.
Okay, it's time to read the Galileo official status, which actually, unless I read this, it's not official, but project engineers report that the spacecraft's rocket fired on time at 5:20 p.m. Pacific Standard Time and stopped 49 minutes as planned, stopped after 49 minutes as planned at 6:08 p.m. Pacific Standard Time, enabling the spacecraft to enter orbit around the giant planet and begin a 2-year mission of scientific studies. So there it is, it's official. We've now read the press release and we are in orbit.
By Jove, that's
we've been in
precision.
orbit. And so what else?
We're winding down, and I wanted to say on air that having watched intermittently during the day this particular program, I think you've done an extraordinary job, Rich, in conveying in a straightforward and a way, not talking down to the audience and not oversimplifying either. And conveying the excitement, I think you've really done an ideal job, and I just wanted to congratulate you.
Well, thank you, Carl, and I'll pay you for that comment later. Thank you, I appreciate that. Torrance, you've just give me a personal perspective on this. What time did your day start today?
I actually got up pretty much at the normal hour because I knew we'd be going by Europa's orbit at 6, so that was okay. And then I got into the lab and started checking in on how things were going, found out that the spacecraft was doing what it was supposed to, and started getting a little more comfortable. By noon, when we were by Io and everything was still going well, I was feeling good. getting that probe signal confirmation was really a high point. Now, here we are in orbit. It's fantastic.
It is fantastic. We're going to go again to David Seidel at the navigations area. David?
Yeah, Rich. Well, I think it's important for my team here to point out that they actually started clamping before the MSA did. They saw in their data, the high-resolution data and tracking plots that they were doing, that the spacecraft was in orbit and the burn had taken place. And the M&Ms are gone. They've broken out the lemonade here, and it was very exciting being here for this event. And of course, everybody's really happy and celebrating, looking forward to a really challenging 2 years ahead for this team in order to collect the science. And I think the only message that can be left from this lab here is for Carl and especially Torrance, and that's time to go to work, guys.
Okay, well, thank you, David. That's great. Gentlemen, we have a couple last questions from the internet here. Torrance, you want to field these? One of them is, what is the Galileo core made of? Or will Galileo determine what the core is made out of? I think I know the answer to that, but I'll let you answer.
The core of Jupiter.
Core of Jupiter. Yes, and the answer to that is that will remain a bit of a mystery. We will get new data to infer what that region deep inside Jupiter will be like. But we will, of course, not measure it directly with the probe, and we have no instruments to measure that directly. That still is in the realm of taking data and putting them into theories. The second question would concern the vaporization of the probe and how hot the atmosphere of Jupiter had to be to do that. By the time the aluminum and titanium is melting, we're down at thousands of bars of pressure and thousands of degrees centigrade temperatures. And it's amazing to think that that probe that was up in the cold upper stratosphere of Jupiter at 3 o'clock this afternoon got so rapidly to those depths in the atmosphere where that would happen.
Yeah, that's really amazing. And it's about 8 hours or so until the aluminum finally, the titanium finally vaporizes.
That's correct.
And there's basically nothing left of the core, except of the probe, except being part of Jupiter.
And indistinguishable from all those other atoms, of which there must be many, of titanium and aluminum and
That's right. There's
other stuff.
There's nothing new that Jupiter hasn't seen before, and as you pointed out to me earlier, that Jupiter is constantly being bombarded by a mix of things, of cometary material. We've seen that with the comet Shoemaker Levy 9, and
as Carl said, Jupiter's seen this before. It just hasn't seen something coming in from this particular point of origin before.
That's right.
That's right, and in this particular arrangement of atoms, it's certainly right.
Okay, any closing remarks that you'd like to make on the...
I started my scientific career looking at Jupiter, still very much like Carl's analogy of the ancient astronomers, as a point of light. And they really became, Jupiter and the system around Jupiter became a place with Voyager. And all I can say now is it's nice to be back in the neighborhood.
Yeah, it certainly is. Absolutely. Carl?
I guess all I'd like to say, beyond my absolute delight after spending 20 years off and on this, that it's working, is that I hope the sense of excitement and the great discoveries that are surely ahead of us will convey to the American people and to those who control the purse strings the importance of continuing the very basic human activity of exploring places we've never been before.
Absolutely. Again, thank you very much for coming here. I appreciate that. We'd like to thank everybody out there in guest operations, our visitors to the lab, in particular the family and friends of the teams of people who've put together Galileo, because without the support of family and friends, it just would have made the job that much harder. And finally, I'd like to close with a personal observation of today's events. I hope you've been watching this program because you're curious, because it's that quality that has really built our world. It drove us to make the tools from rocks initially, to explore our planet, to find new ones, and build machines like Galileo to explore them. But Galileo is more than just a piece of machinery. It's also a symbol. It is a monument to human curiosity, a test of our technology, and an extension of our brains and senses into the frontiers of exploration. I hope you will continue to be curious and follow this adventure as it unfolds over the next 2 years. All of Galileo's messages of exotic worlds and fantastic landscapes are gifts we should all share and pass on. Because we go to Jupiter not for our scientists and engineers, but for all of us, and especially for our children. This is Rich Terrell, an astronomer at the Jet Propulsion Laboratory, thanking you for watching on behalf of NASA and the Galileo project. Good night.